Hello, everybody. My name is Taufeeq Dhansay from the Council for Geoscience in South Africa. So we are basically the geological survey, and we do lots of geology in principle. So I'm going to tell you a story about, maybe also about South Africa, I think. We're very pessimistic. We maybe take a step back into time because we still use a lot of coal for energy generation. And when you tell people in South Africa about carbon storage, they do not believe it. So one of the first things is that our rocks are too old. So we're going to try and teach our old rocks a new trick, or at least we're going to try to do that. So in principle, South Africa, at the southern tip of Africa, also quite deep in the global south. So I think a lot of the topics that we've heard about today maybe doesn't necessarily account in the global south, but we try to use this in terms of guiding how we meet our climate change mitigation scenarios. So in South Africa, we're the largest CO2 emitter in Africa, recorded emitter, I should say. So we emit about 500 million tons of CO2 every year. And most of that CO2 emissions are because we generate most of our energy, more than 2/3 actually, from coal. So South Africa is in the top 10 in terms of coal producers. And with regards to our climate change scenarios, we still anticipate to use coal, at least in the next short to medium term. That being said, we are in a very good natural laboratory because the government has basically established that we should cut the CO2 emissions by half in the next 10 years. So we do not know how to do this. And over the last couple of years, CCUS has basically come as a shining light. So we think that CCUS can be a saving grace in South Africa. And for the last 5 years, we've been doing quite a lot of public advocacy, I should probably mention. In fact, so much so that people want the CO2 in the ground like yesterday. So we actually have an opposite problem in terms of generating the technology. So in South Africa, this is what we know about CCUS. All of these blue dots are basically part of an atlas that was done about 10 years ago. And at that stage, we only considered conventional carbon storage. So not a lot of onshore was considered. However, when trying to convince our policymakers, we had to basically include things like coal. So the red on this map shows our major coal fields. And all of these black dots is basically the CO2 emissions. Makes sense, right? So where we mine most of the coal, we also produce most of the CO2 emissions. And the plan was, or the instruction I should rather say, was to make CO2 or CCUS work right there in the middle of the basically the coal fields and also the major emission sources. The problem with this was at that stage, using conventional sources, we did not think we had storage potential. This map basically simplifies the geology, and this shows your major volcano-sedimentary basins. So we had to go back and we had to look at what could we possibly do. So we threw a lot of geology at this area. This is sort of a zoom in. So the red dot is where we considered we might form our natural laboratory. And this is sort of a basement geology. We're looking at a Paleo-Archean volcano-sedimentary basin with lots of old basalts, old large igneous provinces. And fortunately, because there was quite a lot of minerals in this area, we had access to about 1,500 boreholes, on average between 1.5 and 2 kilometers deep. This is sort of just a map showing you some of those boreholes. We also had quite a lot of legacy 2D reflection seismic data, aerial geophysics, high resolution. So what we did was we took some of those boreholes, not all 1,500 boreholes, but as many as we could, and we scanned them with a hyperspectral scanner. And essentially this allowed us, I mean, one of the reasons I should mention this, I think for the geologists, if you try to log basalts, I mean, it's quite tedious, they're all gray. So fortunately, we ran them through the hyperspectral scanner, and it did most of the work for us. And essentially, we were able to develop this type of a geological profile or knowledge of the area. This is sort of north to south going across this area, roughly about 25 kilometers. And essentially, we identified we have quite a thick package of basalt. This is our large igneous province. And we also found, in addition, some deep saline fractured reservoirs, highly brine-rich 2 billion-year-old seawaters. That was obviously non-potable, and we started thinking that we may be able to develop 2 reservoirs, maybe just a little bit in terms of the tectonics of the area. This is a major discontinuity once you get above the green stuff. So most of the structural controls in terms of fractures and faults, they are restricted in basically the yellow stuff and the green stuff. In terms of thicknesses, this is minimum 200-meter thick rocks. And so we realized we may have an opportunity to use this as a storage locality. We then started doing some of the reservoir characterization. Again, we did a lot of stuff as much as we could. First two problems we discovered was that obviously the basalt being old, the permeability was very low, restricted to fractures. The second thing was, in general, the porosity was not always high. So using the hyperspectral scanning, this is the log. I think this is my log, actually. So when I logged this, I just made it green because it was basalt. But fortunately, with hyperspectral scanner, it started picking up these zones. Essentially, we're summarizing this in terms of reactive zones and non-reactive zones in principle. But the key thing was that some of these zones, we actually found that the porosity was reasonable, up to 10% in many cases. And in fact, some of these areas, there were in fact fractures that we thought we could harness. So in principle, we started finding that we do have lots of layers between reactive, non-reactive, number one, which we also thought could be capping capabilities. We wanted to assess, do they have the minerals that could be reactive? And fortunately, from the hyperspectral, we used the low wavelength infrared spectrum to actually find these mafic silicate minerals. So what this graph actually shows you is the proportion of mafic silicate rocks, reactive rocks in principle. And basically, as you go through some of the higher sequences, which is mostly dolomites, you can see that there's not much mafic silicate minerals, but once you get to the basalt, there's a huge spike. And again, because they change between sort of reactive and non-reactive, this seemed to be a good target horizon. We then sampled as much as we could, and in general, we found that we do have some mafic silicate minerals, mostly pyroxenes, very little olivines, I should mention. And we also did some geochem. So we found that in general, this basically plots as large-scale continental flood basalt, as you would expect. Keep in mind as well, we also did the hydrogeology. That's when we found essentially these 2 billion-year-old seawaters, very, very deep. Because we had to deal with the fractures, we started looking at how could we actually harness these fractures. So we did quite a bit of geomechanics. In principle, our site is over there, and we sit on this ancient craton, so quite deep. So all of basically the ground below here is roughly 250 kilometers deep. However, we do sit at these sort of ancient boundaries of the craton. And what we found is that the stress patterns, these beach balls basically just highlight the stress patterns, basically changes along these deep structures. So what we were able to do was, using some of the seismic data, we picked up what exactly are the deep structures in the reservoir, and we then established what are the major planes, essentially, the permeable horizons, and then we essentially worked at what do we need to do to make them pop, essentially, to increase the permeability, of course. So we found that we can work with pore fluid pressures of around 14 megapascals, and what this basically means is we could probably start to do soft cyclic injection, essentially, to increase the permeability, access the reservoir, and take advantage of all of these rocks. So what does this actually mean? We can now say that we have, at least in this area, this proposed pilot site, we have about 100 cubic kilometers, essentially, of reactive rocks, number one. That's only the reactive rocks. It also includes the deep saline reservoirs. Based on that, we were trying to do some estimations in terms of South Africa's own so-called just transition, keeping in mind how pessimistic we are. So we considered that if you look at a carbon tax of around $50 per ton, South Africa's current carbon tax is an order of magnitude lower than this, but there is ambitions to increase. We could generate essentially a carbon economy of around $1 trillion US. That was essentially the number we put forward. So we actually used a different approach, by the way. We didn't use volumes. We decided to convert everything into dollars because we thought that might actually help a bit. In addition to that, we decided not to use the gigaton, but we actually then presented this as is, that if South Africa emits 500 million tons per annum, this reservoir, the one reservoir, could actually mitigate, theoretically, all of the annual emissions for the next 50 years. It was a bit of a different way, but that's where we got a lot of the support. And of course, that's where essentially we got the support we needed, where they want the CO2 in the ground like yesterday. In fact, they want other people's CO2 as well when they thought of these numbers. But in addition to that, there's a slight complication because this area is very heavy in terms of petrochemical industry. So we then started looking at the utilization component. We do know that there are signatures of white hydrogen in this area because of the basin, the actual geology, and because there is an existing infrastructure for petrochemicals, we realize there's an opportunity to look at things like methanol production. So we're starting to sell that as well as an idea. And essentially what our plan for the next steps is to actually generate some type of a hub. So we have our site as a major CCUS hub. We actually have, I didn't mention this, but we have apparently the single largest point source emitter in the world, which is a petrochemical coal-to-liquid plant. They actually emit, I had to check this, 64 million tons per year, the site over here, and they produce about 99.6% pure CO2, which currently goes into the atmosphere. So with the carbon tax that South Africa has imposed, they will go bankrupt, essentially. So obviously they're looking at this. We also have some coal-fired power plants that are basically due for decommissioning, and we also have lots of mining industries. So we're trying to visualize this as part of South Africa's so-called just transition. In terms of our key next step, we have been given a bit of a deadline. Like I said, we maybe have a good problem. We already have received environmental authorization because we started with this public advocacy program. So we have about 2 years to develop the injection well and start pumping. So we are starting to work with some reservoir engineers in terms of designing the well. We have the first case schematic design. So this is sort of what we're anticipating to produce. We do want to go on a deviated well to take advantage of the fractures for the permeability and then try and harness essentially the well. And essentially we think, we really strongly feel that this might be a very good solution as part of South Africa's just transition, considering the hard to abate, coal industry. And then finally, I should also mention, we are open for business. So one of the reasons we came here was to try and promote collaboration at least. It's very difficult to work with South Africans, I think some of you know, but we will try, we'll try to ease up a bit and hopefully assist in terms of the just transition debate. Thank you so much.